Hey guys, in this video, I want to talk about the common ion effect and some other things that affect solubility as well. So first, let's talk in terms of Le Chatelier. You're probably going to hear lots of dogs and cats and everything running around because I'm in my living room, and usually I lock myself in my office. Don't feel like going up there right now, so my chihuahua is pretty moody right now, so if you see him, he's being weird. All right, so I swear my dogs aren't killing each other. He's just moody. Okay, sorry. So the first thing is effect on solubility. So let's talk about some things dealing with Le Chatelier. So the first thing is dealing with temperature. Now remember, we dealt with this in the other K videos or lecture as well. So if we have a temperature change, it depends on whether or not the reaction is endo or exo. Remember, if it's exo, delta H will be a negative quantity, and that means, Nico, stop, that your heat will be a product, okay? So heat would be a product if it's exothermic. And if I increase temperature, what that is going to do is shift towards my solid. Now we need to learn some terminology here, okay? If my reaction shifts to the solid, then you are less soluble. So if I shift towards the solid, it is less soluble. If I shift towards the ions, however, the aqueous things, so I'm going to say aqueous, towards my aqueous, then that becomes more soluble. So when they talk about Le Chatelier stuff here, then they're talking in terms of you being able to explain if things are more soluble or not. So exothermic heat's a product. If I increase my temperature, then my reaction will shift to the reactants. Because it shifts to the reactants, it means that the reactants, or the solution, I should say, is less soluble. Now, the opposite happens if it's endothermic. So if you have an endothermic reaction, you have positive delta H, and that means that heat will be a reactant. So if heat is a reactant and I increase temperature, so there's my heat here, I increase temperature, my reaction will shift to my product side. And if I'm shifting to my product side where I'm making more aqueous things, more ions, then that means that it is getting more soluble. So that's the effect of solubility and temperature. First, it depends on if it's endo or exothermic. If you increase temperature, which way does it shift? And then being able to determine what's happening from there. For the next thing, number 2, that is adding an acid or a base. Now, when you add an acid or a base, you're going to be working with reactions that have either OH or H plus in it. So that's what we're looking for. If I add an acid contains an H plus. Now, I know we haven't talked about acid base yet, but this will make way more sense whenever we get to that unit. So if I add an H plus, what's going to happen is this H plus and this OH are going to get used up to make water. Now, if this is being used up to make something else, what that means is that my product here is going to decrease. And we all know what happens if I decrease or remove something. So if I remove something, I'm going to shift my reaction to the products in this case. And then if I'm shifting to the products, that means it's more soluble there. So this is if I added an acid to this particular reaction. Now, if I had some H pluses here and I added an acid, that would be a different story. And that kind of is the same situation as if I added a base to this. So let's talk about that. So let's say I added a base to this reaction. When I add a base, what I'm adding is OH minuses. So you see I'm adding the same stuff over here. What that means is that I'm going to increase this concentration. And if I increase the concentration of this product here, my reaction is going to shift to my reactant side making the solution less soluble. The next thing is adding a common ion. So what I see here, if a base is added to a base that's already there, that's kind of like the common ion effect. All right, so common ion, what does it do? Hey, hush. Y'all chill. Sorry. When I'm adding a common ion, then that could be, I can add more OH minuses, or I could add more Mg2 pluses. So when I'm working with that, if I add either one of these, then that's going to cause my reaction to shift to my reactant side, therefore making it less soluble. So adding a common ion, you can work with that conceptually to working with Le Chatelier's principle to figure out which way your reaction is going to shift, and therefore deciding of whether or not the reaction is going to be less soluble or not. What I also want to get to is the mathematical portion of the common ion effect here. So give me a second to get to the next page. I'll tell you which page I'm going to go to, and then we will do an example problem with this. All right, so where I'm at is page 4, the bottom of page 4, exercise 4. And it says solubility in common ions. So we want to figure out the solubility, so remember this means X, of solid CaF2 if my KSP is this value, and it gives us some other piece of information. So let's start by writing the reaction of CaF4. So CaF4, I'm sorry, that's not F4, that's F2. Sorry, it's been a long day. So Ca2 plus 2F minus would be my reaction here. And then let's go ahead and let's finish out my Rice chart. So 0, 0, plus X, plus 2X, and then we get X and 2X here. Let's also go ahead and write my KSP expression. So KSP is equal to Ca2 plus F minus squared. So we have all that set. This is exactly what we've been doing before, okay? Now, let's look at this piece of information now. So what we want is solubility, and it gives us my KSP. But what's different in this question and then exercise 3 that we worked out in the last video is that it is giving us a concentration of some solution. Now, this solution has something in common with our reaction here. And what's in common is the F, all right? So this F and this F are in common. So that's why we call this a common ion. Now, when they give you a concentration of a common ion, what that does is take the place of whatever this expression would be. That's not equal to 2x. It takes the place of 2x. Very important to know. All right? So the reason why it totally replaces 2x is because this 2x value will probably be so much smaller comparatively. So we say that this is 0.025, and that's not equal to 2x. It's just the concentration of F minus that you have. So I'm going to say now that F minus this concentration is 0.025. Now, I do not know this value for X. This value here has no relation now to this value here. This is where some students get messed up. Okay, this value from the common ion has no relationship with this X value. So in order to solve for X, I'm going to have to plug in my KSP value, which is 4 times 10 to the negative 11. And I'm going to have to plug in my Ca value, which is just X, what I'm solving for. And this F minus value, which is 0.025 squared. Okay, so I take this value that's from my common ion and I directly plug it in for my concentration there. I still work with the square because that's where my coefficients come into play. I do not double that. You see how I didn't say 2 times that value? I just directly replace that. Now what I'm going to do is solve using algebra for my x value. And when you do so, you get 6.4 times 10 to the negative 8th. Okay, so this is called the common ion effect. This is a mathematical thing. You can see it on multiple choice as well as see it on free response. And how I know it's a common ion question is because you're solving for solubility, you're given a KSP value, but you're given another piece of information. And that piece of information has something in common with what I have in the reaction. So that's how I know to use this approach. So I hope this is helpful, and I'll talk to you later. I'm sorry for the dogs, by the way.